Okay, it's noon hour. So, first of all, do you guys like having the lights off over here? It's probably easier to see the screen. Is that better? Raise your hand if you think it's worse. So, who thinks it's better? Okay. So, looks like majority rules. The ones that say it's worse, can you move up closer, or there's seats in the front? But anyways, let me talk about the schedule real fast. I know the test was originally scheduled for Wednesday, delayed a week, so today we're going to finish chapter 4. We only have a little bit left. Then I'm going to go into chapter 5. Chapter 5 is not on the test, just chapters 1 through 4. And then when would you like to have a review? Do you want it Wednesday or Monday? I'm inclined to go Monday. Or would you prefer to have it this Wednesday? What do people feel like? Today? I'm not prepped for today. So I guess we can do, or should I have to keep on trying to vote? Who would prefer Monday for a review? Okay, that's more than half the class. So majority rules. All right. So we will go on today, then once we're done with chapter 4, we'll go into chapter 5 then also on Wednesday, but remember it's not on the test. What you'll be given, so the test is going to be 20 questions, multiple choice, lots of space on the test. You can show your work for partial credit. You will be given a periodic table, any constants and or equations you need, well both actually, constants and equations. You will have all those given. You don't have to memorize any of those. So, and I'll go over the previous test. The review is going to be going over a previous semester's test on Monday. Question, America?
Electron tendencies, group and periods. Is that going to be on this particular periodic table?
What do you mean by electron tendencies?
Like group 1,
sodium tends to be +1, you mean?
Yes.
Yeah, that concept will be there. Yeah. But I mean, it's not going to be tested on exactly. It's not saying, what's the charge of a sodium ion? You'll have to know it. And what was the other question?
Yeah, just if like the periods, the main groups are going to be denoted, or.
Not necessarily.
Okay.
I mean, but you're also in the online class, so you're going to have a different test.
Yay.
So, anyways, all right. So, any other questions? This is where we left off, was talking about oxidation states. And if you were in my lab, we had hexavalent chromium +6, and it's a carcinogen. So bad stuff. You ever seen the movie or heard of Aaron Brockovich? That was the stuff that gave people cancer. Chromium +3, though, is completely safe. So they put chromium +3 in certain types of glass. And some of the oven glasses have chromium +3 in it. It's totally fine. Chromium +6, though, stuff's really nasty. Gives you a rash and gives you cancer. Okay, so oxidation states, these rules are hierarchical. So meaning the rules are more important in order. Oxidation state of a free atom is 0. A free element, I should say. Oxidate for a monatomic ion is equal to charge. Sum of oxidation states, neutral molecule or formula unit, 0. Ion, the charge of that ion. Alkalis are +1 in compounds, alkaline earths are +2, and then we have this chart. And oxidation state rules are also something you do not have to memorize. So you'll be given this chart. Okay, and this is where we left off. Assign oxidation states. Chlorine, free element, it's 0. Sodium, monatomic ion, +1. Potassium fluoride. Potassium plus fluorine equals 0. So the oxidation state for potassium, oxidation state for fluorine equals 0. Potassium tends to be +1. As it is an alkaline earth, that's rule number 4. And then potassium being +1 makes fluorine -1. So carbon dioxide, Carbons plus 2 oxygens equals 0. I'm getting the 2 from the 2 in carbon dioxide. Then oxygen tends to be minus 2, which then forces carbon to be plus 4. So have we any questions with this so far? Sulfate, similar, this is where we left off. So similar to carbon dioxide, but instead of it being 0, it's minus 2 for the charge. So then oxygen tends to be minus 2. Sulfur plus 4 times minus 2 equals minus 2. Sulfur plus 4 times minus, plus and minus 8 equals minus 2. Add 8 to both sides, sulfur is 6. So plus 6 minus 2, like that. Is this making sense? Okay, potassium peroxide, same thing. So 2 times potassium plus 2 times oxygen equals 0. So potassium, if you look at the rules here, rule number 4, with the alkalis being plus 1, is greater than oxygen being minus 2. So this is 2 times plus 1 plus 2 times oxygen equals 0. And then you see where this is going. Oxygen is going to be equal to minus 1. So this is going to be plus 1 minus 1. So you're like, wait a second, why isn't oxygen minus 2? Well, if you put in minus 2 for oxygen, the potassium, 2 potassium plus 2 oxygen, 2 times plus 1 plus 2 times minus 2, that's going to be equal to minus 2. That would be true if this was a minus 2 ion, but it's a neutral charge. So oxygen can be minus 1, and the term that we call things in the minus 1 state, oxygen being in the minus 1, are peroxides. So hydrogen peroxide, H2O2, that's oxygen in the minus 1 state. So why do we care? Peroxides are very reactive. In particular, they can be explosive. We can also have fractional states. You can have oxygen in the minus 1/2 state, so you can have even fractional oxidation states. Oxygen in the minus 1/2 state, that's called a superoxide. And if peroxides are reactive, superoxides are even more reactive. So these are very, very, very reactive. And so why do we care? Well, they can be explosive. So diethyl ether, if you've ever heard of diethyl ether, it's the stuff that Fear and Loathing in Las Vegas, the guy did a lot of that in that movie or book. But when they have diethyl ether, they put certain compounds in it to prevent the formation of peroxides. Because there's been issues that if people pick up the can, so there's usually in a metal can, if you pick up the can and you bang on something, it could explode. And diethyl ether is very, very flammable. Another thing with hydrogen peroxide, it reacts very well with metals. So usually when you get hydrogen peroxide, it's in a plastic bottle. You're like, oh, why would I mix it with metals? Well, they use it in hair dyes. So, and some hair dyes are metallic. So one of the most common hair dyes is something called the Grecian formula. It's lead acetate. It turns hair black. So it's really common to turn gray hair black. And if you have someone who colors his or her hair with the black lead acetate, and then the person goes to a hair salon and tries to get some other color done, peroxide, usually the organic dyes, carbon-containing dyes, are mixed with peroxide. If the stylist were to put that dye right on the person's head, the hair could catch on fire. And that's pretty common, actually. What they're trained to do is do what's called a spot test. You do a little spot to see if it sizzles. But if someone is mixing it up, you can mix it up, and they have to use plastic bowls too in a salon. So if you see a metal bowl, that it may not react right away, but it can also create explosive compounds. So they've done that practice, but it could explode. So but some people still do it anyways. But with the metallic dyes and hair, that can really go. There's also some dyes that use silver and nickel. So silver, unfortunately, they turn hair sometimes blue and kind of green colored too. So if you ever see an older person with a funky looking metallic blue color, so that probably is like a silver dye that went bad. But it's usually, you find it usually more in older people. You don't see the hair dyes today are much more commonly organic, so carbon based. Okay, so let's look at some of these other rules, or not the rules. What are the oxidation states of everything in potassium dichromate? So what do we know? Potassium tends to be +1. That one's easy. Oxygen tends to be -2. So this is the 2 times potassium plus 2 times chromium plus 7 times oxygen equals 0. That rule. And we put in what we know. 2 times +1 plus 2 times chromium plus 7 times -2 equals 0. So 7 times -2 is -14. This is 2. So then 2 plus -14 is -12. So 2 times chromium is +12, or chromium is equal to +6. You don't have to use the plus, I'm just doing it for emphasis. So then chromium is +6. And that's also when I told you this stuff is nasty. This is the chromium, the hexavalent chromium, the stuff that will give you a rash and give you cancer. So chromium compounds also tend to be very yellow. This stuff is very, very yellow. It's like a minion kind of yellow if you like the Despicable Me colors or whatever comic. All right, so how are we doing? Questions? You see my procedure in that?
I'm trying to figure out like the basic math here.
The basic math,
Yeah,
okay.
so we've got 7 times -2, so that's going to be -14.
Yeah.
And then add 4 to that?
So another line here, if you want another line.
Yes, please.
2 plus 2 times chromium minus 14 equals 0.
Okay. So you're
Equals 2Cr minus 12 equals 0.
okay. Got it. Thank you.
Other questions? So what is the oxidation number of manganese and potassium permanganate? Purple stuff. Potassium tends to be +1. Oxygen tends to be -2. Some people think it's 0. How many think it's 7? How many think it's 8? I think it's 14. Anyone getting stuck? Just need more time, okay. Because greater than half the class is going for 7. 7 is the right answer. So if not, I'm gonna move. Anybody want me to go around? Okay. So this tends to be +1. So 0 is equal to potassium plus manganese plus 4 times oxygen This tends to be plus 1. This tends to be minus 2. So 0 is plus 1 plus Mn plus 4 times minus 2. So then you have 7 is manganese. Like that. So questions with this? So one of my guilty pleasures is this. Oh, it needs to be updated. Oh, it doesn't work anymore. Oh, I can't play that game. It's a game that uses oxidation states to solve puzzles. But unfortunately, I can't play it for you now. Oh well. Just imagine having a lot of nerdy fun. Okay. So still an oxidation reduction. So redox, that's oxidation reduction. So we have this reaction here. We have magnesium metal, 2 waters to make magnesium hydroxide and hydrogen. So if you look at the oxidation states, magnesium's a free element, oxidation rate 0. Water, hydrogen's going to be plus 1, oxygen's going to be minus 2. Now, magnesium goes in the metal in a compound now. It's an alkaline earth, it's plus 2. Hydroxide, oxygen's still minus 2, oxygen's minus 2, hydrogen's plus 1. And hydrogen's a free element, oxidation state 0. So looking at this, magnesium goes from all of its electrons to missing 2. It is oxidized. It loses 2 electrons. Hydrogen goes from the plus 1 state to the 0 state. It gains electrons. It's reduced. So then you look at this, and students frequently have a hard time remembering this. The species that is oxidized is also known as the reducing agent. It causes the reduction. And the species that is reduced is the oxidizing agent. So I always think of like James Bond. James Bond is the agent of death. He has a license to kill. And if you ever see the movies, he never dies. He delivers. He's delivering the death, right? So the reducing agent delivers the reduction. It itself is not being reduced. It's causing the reduction. How does it cause reduction? By being oxidized. Reduction means getting electrons. So a reducing agent gives electrons. And an oxidizing agent oxidizes by accepting electrons. It takes electrons away. That's the oxidation. So, and anyone can guess what the most common oxidizing agent is? That's not water. Oxygen. Oxygen is by far the most common oxidizing agent. Anyone want to guess what the most common reducing agents are? It's not magnesium. Fuel. Fuel is a reduced form of matter. So whether it be gasoline, oil, kerosene, or in our own bodies, sugar and fat. Those are all, well, I guess even protein can be reduced. But sugar is our most common fuel, so reducing agent.
So why are magnesium and hydrogen zeros in this?
They're free elements. So if you remember the rules,
Okay.
a free element is, it's the rule number 1.
Got it. Thank you.
Other questions? Okay. So glucose. Glucose plus oxygen makes water and carbon dioxide. What is the reducing agent? How many people think A, it's sugar glucose? How many think B, oxygen? Well, it's not water or CO2 because they're on the wrong side of the equation. It has to be one of those two. So do you want to know the oxidation states? Would that help you? Carbon is 0. This is +1. That's -2. That's 0. That's +1. That's -2. That's +4. That's -2. I always thought it's kind of cool that carbon is 0 state in sugar. Some people think that glucose is the reducing agent. How many think that oxygen is the reducing agent? Okay. So, what did I say were the most common reducing agents? Fuels and sugars. What did I say was the most common oxidizing agent? Oxygen. You are literally adding oxygen to this, right? Plus O2, adding oxygen. This is oxidized. This is reduced. This goes from 0 to +4. Carbon loses 4 electrons in this process. So this is being oxidized. This is being reduced. It goes from 0 to -2. So it's gaining electrons. So since this is being oxidized, it's the reducing agent. It is causing reduction. Oxygen is being reduced. It's the oxidizing agent. People are getting me kind of... Most people are happy. Some people have a blank stare. What are the blank stare folks thinking? Think of it like opposite day. Like, say I'm a womanizer. I'm not, but I'm a man, right? I kind of like it's like the opposite like that. Like, what's being reduced is actually causing oxidation. And the same thing, what is oxidized is actually causing the reduction. So, because when thing is oxidized, it gives off electrons, and the act of giving off electrons causes something else to be reduced, because reduction is absorbing electrons. So, and vice versa. So. Questions? No questions? Okay. Yes?
On the test, are we supposed to know how those elements recombine?
What do you mean by how they recombine?
Like, if we're given two elements that are reacting together like that, are we supposed to know what they're going to react to?
No. Unless it's a precipitation reaction. But then you'll be given a chart. For oxidation reduction, no. But for precipitation reaction, yes. But you also be given the solubility rules, so you should be able to figure out if something is going to be precipitated out. And you just had a lab on that too. Other questions? Okay. The thing is that if you're just given two reactants, there's more than one possibility for a product. So, like if you take sugar and you add oxygen to it, this doesn't necessarily have to form water and carbon dioxide. It can form carbon monoxide, for instance, depending on how much oxygen is present. And it can form many other compounds. You could make caramel. So, and actually caramelization is not a very well understood reaction. So we know it works, and we make lots of it, right? And you can make it in your kitchen, but we don't really understand exactly how caramel forms. So, and caramel is also a mixture. It's not one thing, it's a mixture of things. So, other questions? Okay, so we are done with the stuff for this test. So what we're going to talk about today will not be, or after the oxidation reduction stuff will be on the test. The gas law stuff, which I'm going to talk about today and Wednesday, is not. So, okay. But So you can kind of relax your brains a little bit, but not so much that you, because this will be on the next midterm. Yes, chapter 5. Yes. Okay. So let's say I want to go snorkeling, but I'm going to go deep, deep down, and I just want to stay down. What if I just got this huge 100-foot-long snorkel and dove down and then wanted to snorkel underneath 100 feet underneath the water? Will this work? Will I be able to breathe with a 100-foot snorkel? So why not? Boyle's law, yes. I heard pressure and Boyle's law and a couple other things. Here are my lungs. 100 feet of water, so 33 feet of water equals 1 atmosphere of pressure. So that means that there is 1 atm from the atmosphere, and then 3 atmospheres from the 100 feet. So that means the pressure down here is 4 atmospheres, and the pressure up here is 1 atmosphere. If you push down on something at a pressure of 4 atmospheres, and you have an opening that's 1 atmosphere, what's going to happen? It'll collapse the lungs, right? So basic things with flow. I know we don't talk about many engineering concepts. Well, I do, but the book doesn't. So the reason why things flow, it's always from high pressure to low pressure, high temperature to low temperature, or high concentration to low concentration. So if I want water to flow into my mouth, right, I bring it up high, so then the pressure, it's by gravity. I don't spill it on myself there. So just like with a faucet, up high, coming downhill, the pressure gets lower. So water will flow out of the bottle. It won't flow up into the bottle, right? So you don't go the other way. Same thing with temperature. You put your ice cream in the oven, you turn the oven on, the heat flows from the oven to the ice cream. The heat doesn't flow out of the ice cream to make it colder and make the oven warmer, right? Heat always goes from hot to cold. Pressure always goes from high pressure to low pressure, and things go from high concentration to low concentration. I open up a bottle of perfume, the smelly perfume goes into the room. That works, that does work. I can't go into a room full of perfume, put a bottle in there, come back an hour later, and then all the perfume is in the bottle. That doesn't work that way. Always goes from high concentration to low concentration. So that's the basics of flow right there. So if you have a high pressure situation, like deep down underwater, and you try to breathe, you'll just force all the air out of your lungs. So that doesn't work. And we also mentioned pressure. What is pressure? Pressure means force per area. So I should write this out. Force per area. Yeah. So like PSI, this is equal to pounds per square inch. So 1 PSI is literally the force of a pound. So my thumb is about a half a square inch. So if I put a half a pound of force over my area of my thumb, this is equal to about a pound per square inch, 1 PSI of pressure right there. And an atmosphere, so 1 atmosphere is 14.7 PSI. So the atmosphere, that's the average pressure of the atmosphere of the Earth. So the SI unit, the metric unit, System International Unit, is a Pascal. So that's 1 Newton per square meter. A square meter is about this big. So 1 Newton, and Newton is not that much of a force. Newton is a pretty weak force. So, and it's 101.3 kilopascals. So it's about, so that's about 10,000 10,000 pascals is an atmosphere. Well, it's 1.3. I'm sorry, it's 100,000. It's 101,300 pascals is an atmosphere. So what's also interesting, so United States, our standard state is 1 atmosphere. If you go to Russia, their standard state is 1 bar. So we're close. A bar is 100 kilopascals. But we can talk about that later when we get to standard states. Bless you. Now, where was I talking about pressure? Also, sound. Actually, no, let me go back to talking about pressure. If you ever do plumbing work, or if you talk to firefighters, so they teach firefighters how to do really quick calculations. So of course, if you're a firefighter, one of the most common ways to put out fire is to spray water on it. Surprise, surprise. And I told you 33 feet of water, that's an atmosphere of pressure. So in 15 psi, that's an atmosphere of pressure. So that means 15 psi of water pressure, you can shoot water 33 feet with that, with 14.7, but 15 psi. So if you want to pump water uphill to 100 feet, you need 15 times 3, you need 45 psi. So if I am a firefighter and I'm shooting water, I need to shoot water up 100 feet, I know I need about 45 psi of pressure. And that's a pretty strong hose. So you need to have a lot of people. You'd probably need 5 or 6 firefighters holding onto that hose to have that much pressure behind it. Also for plumbing. So I have a building and I have a high rise, and so how can I ensure that the water can go up all the way to the top of the building? That's the calculation they use. They use about 15 psi per 100 feet, and whatever that turns out to be. I mean, it's really, like I said, 14.7, but engineering terms, the error is acceptable for that. So, okay, other things with pressure, a sound wave. A sound wave is a pressure wave, and it's specifically, well, it works in your ears. It's also known as a longitudinal wave. So later on, we're going to talk about light. So light is a transverse wave. Ocean waves are transverse waves. A transverse wave means that the displacement is perpendicular to motion, right? So an ocean wave moves this way. You yourself go up and down, perpendicular to the motion, right? A sound wave, it's the air, there's a pressure wave. The pressure wave moves in the same direction as the sound. That's called a longitudinal wave. And how our ears work is we have our eardrum, and then the other 3 is like hammer, sickle, and I forget the name. And stirrup? I don't know.
Yeah, stirrup.
Yeah. Right, but the eardrum, it feels the pressure wave, and then it carries it through the bones, which then go into the hairs or what.
Circular canals.
Yeah, there you go. I'm really terrible at biology. So yeah, and then you can send a signal to your brain from that. Right. So sound is a pressure wave. It's a like I said. Okay, and then someone mentioned Boyle's law. We're talking about that. So what I'm going to build up to is what's called the ideal gas law. Next. So Boyle's law, we're going to have a lab on this. So Boyle's law, and this is a scientific law. A scientific law, if you recall, is a summary of observations. So you make a bunch of observations, and you can summarize them into a scientific law. Boyle's law is that pressure and volume are inversely proportional. So that's what I've written here. Pressure in this alpha, that thing looks like a fish, that means proportion. Pressure is proportionate to 1 over the volume, also known as inversely proportional. I remember in high school it was described this way. P1 V1 equals P2 V2. So what is inversely proportion? It's kind of like my bank account balance versus how much fun I'm having. So let's say I'm having lots of fun. I'm traveling, I'm going out to eat, I'm going to concerts, having lots and lots of fun. What happens? My bank account balance goes down, right? Because I'm spending lots of money. let's say that, I'm going to stay at home and eat crock pot meals and watch Netflix. So that's pretty cheap. So what happens to my bank account balance? It increases, right? So you could kind of say that my level of fun that I'm having is inversely proportional to my balance in my bank account, kind of, sort of, until I have to pay my taxes. But that's fun, right? Yeah. So okay. Then there's also these other laws. Charles' law. We don't have hot air balloons here. Charles' law is that volume is directly proportional to the temperature, which means if the temperature goes up, the volume goes up. Or also if the volume goes down, temperature goes down, or the volume goes up, temperature goes up. So that is Charles' law. And that is how a hot air balloon works. A hot air balloon works by, like I said, you don't have them here, but this is a classic example for Charles' law. You have a real droopy hot air balloon, and what do? You have a fire underneath it. Usually use some sort of propane or some sort of combustible gas. And what happens? Well, the balloon gets bigger. And then now the whole thing can float via buoyant force. Right? So Charles' law, that's Charles' law there. Volume is directly proportional to temperature. So, okay. Now, the other thing with temperature, we use in this, you have to use what's referred to as absolute temperature. So notice there I have K for Kelvin. K, that's Kelvin temperature. I have degrees Celsius, then plus 273.15. So notice a couple things. First of all, Kelvin does not have a degree sign. So a degree, when you have a degree unit, that means that you relate it to something else. So Celsius is related to water. So 0 Celsius is when water freezes at 1 atmosphere pressure. 100 Celsius is when water boils at 1 atmosphere pressure. And then the rest is just incremental divided by 100. And then Kelvin, so 0 Kelvin is absolute 0. So, okay. I already had a discussion about temperature. Do you guys remember my discussion about what temperature means? You guys are looking blank, right? So, remember I could move this way? Any other way I can move? How else can I move? Up and down. This is still translational. Up and down. Any way else I can move? Rotate. I can rotate, and I can vibrate.
Kinetic energy.
Yeah, it's all kinetic energy.
Right.
Yeah.
The temperature.
Temperature.
Yeah.
Temperature. Definition of temperature is average translational kinetic energy. So if this is a water molecule, it can move up and down, left and right. So this is temperature. So this is cold temperature water. This is high temperature water. Water can also, it will rotate and it'll vibrate. You can't see my fingers. So water is always kind of doing this. Even when it's moving, it's not doing this. It's vibrating, it's rotating, moving around. Okay, so, but this motion here, moving around, that's the temperature. That's the translational kinetic energy. 0 Kelvin means it's not moving. 0 Kelvin is 0 translational energy, which means it's not moving at all. Okay, so I remember I was a science fair judge, and there was a student that was doing something, and he said, and then the temperature of this will be minus 10,000 degrees. I'm like, sure about that? Because you can't get below absolute 0. Because you can't get any slower than not moving. Right, so that is the absolute 0. It's the, like I said, you can't get lower than that. Okay, so, and absolute 0, it's minus 273 Kelvin. That's about, minus 273 Celsius. There's also, I'm sure everyone here is familiar with degrees Fahrenheit. There's an absolute Fahrenheit scale called Rankine, and absolute 0 is about minus 450 Fahrenheit. So You probably won't see this in any science book. Engineering uses this. So for those of you that are an engineering major, you might see R as a temperature. You're like, what is R? It's absolute Fahrenheit. Okay. Let's see if you're following though. Minus 100 degrees Celsius is what in kelvins? I think it's 173. All right, that's the right answer. All right. Anybody have any questions with that? So when we do these laws, you have to use the Kelvin temperature. Cannot use the Celsius temperature. Very common mistake. Okay. Another law is called Avogadro's law. Avogadro's law is volume is directly proportional to the number of moles. So how do you blow up a balloon? You blow air into it. If you put more air into it, does the balloon get bigger? Yes. That's Avogadro's law. You blow up a balloon, you add more air to it, the balloon gets bigger. Volume is directly proportional to the number of moles. There's other laws too, but I just picked those three to talk about. There's Gay-Lussac's law as well, for instance. And I'm just going to jump ahead to the ideal gas law. Ideal gas law is pressure times volume is equal to n the number of moles. R is the gas law constant times T temperature. So ideal gas law. This is a hypothetical law. So the ideal gas law is not a real expression. So and most of everything we're talking about in this class is ideal. I will talk about real gases at the end, but you're not going to be tested on real gases. And there are better ways to do it than what the textbook does, actually. But we talk about the van der Waals gas. And there's much better ways to do it than the van der Waals equation. That's a terrible equation. Okay, but an ideal gas law, and we'll talk about this when we get to kinetic molecular theory. An ideal gas is one that the particles themselves have absolutely no volume, but the gas has a volume, but what makes up the gas has no volume, and they also have no attraction for each other. So when you have atoms and or molecules flying around, they have a slight attraction to each other. Okay, so they have a electrostatic attraction. So if even something like a xenon atom, has a big electron cloud, and the xenon, the electrons can flow one way or the other, and you can get a partial positive, partial negative, and xenon can actually then attract itself and form things like solids. So xenon has an attraction for each other, and so what? It makes two particles look like less than two particles. So ideal gas law works only by the number of particles. And that's the attractiveness. The other issue is that the atoms and molecules themselves have volume, so which means if you compress gases down really, really tightly, then the actual size of the atoms and molecules then push back, and it makes the pressure look different. So that's your ideal gas law. It's the perfect gas law. It's kind of one of those made-up things. I used to work for Bath and Body Works and Victoria's Secret. That's a company called Intimate Brands. It's all part of the Limited Corporation. And if you ever look at the Victoria's Secret catalog, those are not real pictures. I mean, they're real women, of course, but they airbrush the heck out of everything. Okay, so those are basically digitally enhanced beyond anything you'd ever see. And if you've ever seen a model go to a photo shoot, they always have a ton of makeup on as well. It's not like their real face. And they have them for different colors and that kind of thing. So and the shading is very different. So I mean, that's like, and also that's considered right now to be our idealized beauty is actually a female, like in the
late teens, early 20s, maybe even probably late teens. It's kind of funny, that wasn't always that way. So men used to be the ideal beautified things. So if you look at Michelangelo, like if you ever go to the Sistine Chapel and look at Michelangelo, like basically it's the 18-year-old male, ripped male. That was the most beautiful thing, was an 18-year-old ripped male. So if you look at Michelangelo's Moses, so he has a sculpture of Moses, it's a ripped 18-year-old guy with a beard and horns on his head. It was from a mistranslation of the Bible. So Moses is a ripped 18-year-old guy with a beard with horns on his head. And women were ripped 18-year-olds with breasts, basically. So now we've had a switcheroo in our what we consider beautiful now. And women were considered ugly in the Renaissance. So that was like, oh, you're a woman? Oh, but a beautiful man, that's different. Now it's the opposite, where we see the female form is, at least contemporary-wise, is the more artistic beauty for this day and age. So this artistic beauty, this is like the ideal gas law. This is the most perfect, beautiful gas you could ever imagine. There's absolutely no attraction for any of the particles whatsoever, and the particles themselves have absolutely no volume. And this is mathematically derived. And the next thing you're probably wondering is, what the heck is this R? R is known as the gas law constant. R is actually two other constants. It's the Boltzmann's constant times Avogadro's number. So, Boltzmann. Yeah, that's above and beyond this class, by the way. It deals with probability. So Boltzmann constant is a probability constant. So in future classes, you may get to derive this. It's pretty boring, actually. I don't like deriving things. And this is the value of R here. There are different values of R based off of units. So the units being liters, atmospheres over mole Kelvin, it's 0.08206. It's also, which we'll talk about later in the class, it's also 8.314 joules per mole Kelvin. So if you change the units, you change the value of it. You do not have to memorize any of the equations or the constants. You'll be given them. You just have to know how to use them. Okay. How are we doing? Some more questions? Okay, ideal gas law. Calculate the volume occupied by 0.845 moles. It doesn't matter what gas, it's an ideal gas. Moles of nitrogen gas, pressure of 1.37 atmospheres, and temperature of 315 Kelvin. I should also mention, where the ideal gas law works very well is under low pressure and high temperature circumstances. So right now, like planet Earth, at 300 Kelvin and 1 atmosphere pressure, that's considered high temperature, low pressure. So what's low temperature? Like 100 Kelvin, that's low temperature. And what's high pressure? Like 100 atmospheres, 1,000 atmospheres. So Venus, although Venus is pretty high temperature, it's really high pressure. Venus is around 90 to 100 times atmosphere pressure of the Earth. The ideal gas law wouldn't work very well on the planet Venus. It worked very well on the planet Mars, though. Work even better on the planet Mercury. Doesn't have much of an atmosphere there. And I say it works pretty well. It works on the order of 95 to 98% accurate. So using the ideal gas law actually incurs error. So there'll be a little bit of error. It depends on the conditions, but you will get a few percent error by using the ideal gas law, because gases aren't ideal. Ideal gas law is a mathematically derived perfect gas. Okay, but we're not dealing with real gases. We're dealing with ideal gases. What is the volume occupied by that many moles of an ideal gas at that pressure and temperature? So how do you solve this? PV equals nRT. So, and we're looking for volume. So
volume equals nRT over P. So, and this is one of the things where I assume you can do this. The slow way of doing this, you can multiply both sides by 1 over P, and then these P's cancel, and then that one goes there. Or if you want, you can look at the simulation method. Here's pressure, and it goes root under there like that. So, but this is one of those how to solve for one equation like this and rearranging the variables. This is something that it's assumed you have these skill sets coming into the class. Okay, but so you solve for that, and if you're ever having trouble with it, please feel free to ask and or come and get tutoring if you are getting stuck on how to do that. So we solve the equation to solve for volume, then you just put in the numbers. So this is 0.845 moles. R is 0.08206 liter atmosphere over mole Kelvin. Temperature 315 Kelvin. Out over pressure 1.37 atmospheres. And if you look at the units, the moles cancel there, and this is on the bottom, the kelvins cancel there, atmospheres cancel there, so we're left with liters. Did I do this? I see this. Did I? Oh, no, I didn't. All right, so you put in your handy-dandy calculator. And have two things. This equals 15.9 liters. Oh. All right. Okay, this problem here, ideal gas law. It doesn't really what the identity of the gas is, just the fact that it's ideal. So PV equals nRT is ideal gas law. We solve for volume. We need to know the volume. We have the other terms. So one equation, one unknown. Rearrange the equation. Volume is equal to n number of moles times R gas constant times temperature in kelvins divided by the pressure. So then putting in the values, so 0.845 moles times gas law constant times 315 Kelvin divided by 1.37 atmospheres, and we get 15.9 liters. So questions on how to do this? Okay. Pressure is a half an atmosphere, 0.5 atmospheres. Volume is 50 liters. Temperature is 50 Celsius. What are the number of moles? Some people think A, half a mole, B, 1 mole, C, 3 moles, and D, 6 moles. Okay, so I'm going to come around. So is anybody getting stuck? Raise your hand if you're getting stuck. Just need more time? Okay.
Divide by oh, you divide by RT. Divide by
Okay, the answer is B. It seemed like everyone just needed more time. If you notice a couple things here, well, 0.5 times 50, that's 25, so I just went ahead and put 25 here in the calculator. Divided by R, divided by then the quantity 273 plus 50, this is the right answer, so close to 1. And if you forget to put in the Kelvin, you get 6. That was a misleading answer there, right? So that's one thing with multiple choice tests. Just because you calculate an answer, you could still be doing it incorrectly. So the other thing to note, if you've noticed what I'm doing here, I'm doing divided by things. I'm not going through all the parentheses. I guess I've always just sort of trained myself to put the fewest numbers in the calculator and fewest keystrokes as possible. Let's say, for instance, let's say if I put, instead of that, I put a multiplication symbol there. So the issue with our technology is that it's dumb. It can do calculations really, really fast. Computers are great at that, doing lots and lots of calculations super fast. So, and it can only do what we tell it to do. It can't think, it can't reason. So we can think, we can reason. Computers aren't very good at that right now. But this is the order of operation. So, most of the mistakes I see in students are order of operations. And that's really unfortunate because then they get all the concepts and they get the right numbers in, but they put them in their calculators incorrectly. So order of operation goes left to right. So if you put a multiplication here, what the computer would have done is 25 divided by that number, then this new number would multiply it by that number. So you would get a huge number. So this here would be about 300. If this was a multiplication thing, this expression would end up being 300 instead of 1 because of
Actually, I guess it'd be more than that. Divided by that, it'd be 300 squared. So that'd be about 900,000 or 90,000. So, anyways, yeah. So it's important to know how to put the numbers in your calculator, and that's one of the reasons why I'm making you do this, because that's called a psychomotor skill, psycho brain motor doing stuff. Putting your numbers in your calculator, that's actually an important skill. So I'm glad everyone is bringing his or her calculators to class. So please do that, and if you get a different answer than me, that's a time either when I come around or after class to come and say, hey, what'd I do? How did I screw up? Kind of thing. Because, like I said, the psychomotor skill of putting numbers in your calculator is a very important skill. And from what I understand, they don't really teach that in high schools here. You have a question?
Yeah, the 273 is
Yeah.
the 0.15
It is.
negligible, or it doesn't matter?
It depends on your error. Depends on in your error, which
Oh,
you.
it's almost, I mean, it's 0.942, you see what I mean? Like,
It's like 90.97.
yeah, it's only a difference of, what have you, but like, I have almost the same answer as you, but when you typed it in, it was 273 plus 50 instead of 273.15.
Yeah.
So, I'm just gonna put in the 15.
Yeah, that's fine.
Okay, I just was
That's
making
fine.
sure it doesn't like.
It's a significant figure argument because these are half to whole numbers.
I see why you did. Okay.
Yeah, it just wasn't worth the time to put in the
Okay, that
0.15.
makes more sense then, 'cause I'm like,
Yeah.
did I? Okay.
Yeah.
That makes sense. Thank you.
So like that's the other thing with science, and we don't talk about too much in this class. In 162, we'll talk about it a little bit more. There are lots of shortcuts that we do in our equations. So you probably heard of E equals mc squared.
Yeah.
There are terms that are disregarded in that equation. Energy is not exactly equal to mass equals, and it's not mass and speed of light squared. There are little other terms. If you do that, there's an error involved in that.
Mm-hmm.
And we do certain expressions and we accept the error with that. But it depends also what you're doing. So if you know the Deep Impact Probe, that was a probe where NASA shot up a rocket that had a satellite that shot a projectile that hit an asteroid. Or no, it was a comet, hit a comet, and then looked at the stuff that bounced off the comet. Okay, so the amount of calculations that I do that had to be very, very precise, because you'd probably have to include the gravity of the moon, the gravity of Jupiter, all this other stuff in your calculation. Because if your error was off by like 3 meters over 100 million miles, then you're gonna miss it. So
you would add the 0.1.
yeah,
But that
yeah,
was-
and it would be
totally.
it'd be a much
But
greater
since
numbers.
The answers are coming in.
Yeah.
That makes more sense.
Yeah,
Okay,
so
thank
it's
you.
if it's okay, but you got it. All right.
Yep.
Other questions? If it makes you feel better, just put in the numbers and then round them off at the end.
Either way, you're still gonna have to
Yeah.
pick one of those.
So what I do there, when I cut off answers like that, that's a certain type of error called truncation error. And it's a systematic, or truncate means cut off.
Yeah.
So the truncation error, and it's the error is, like I said, just something you manage. I do lots of truncation. For carbon, I say it's 12 grams per mole. It's really 12.011. And I just put 12. Hydrogen is 1.008. I even know the number, but I don't use it because I just accept the error. Okay. Other questions? It's how a lot of things are done in science and engineering, believe it or not.
That makes sense.
Okay. So where are we? Okay. Here are some here's a derivation. I hate derivations. That's right. Sorry, I shouldn't say that to the audience. Okay, here's a derivation. So, ideal gas law: pressure times volume is equal to number of moles, R gas law constant, times the temperature. M molarity, as in moles per liter, equals number of moles divided by volume, so you can rearrange that to pressure and molarity, also known as moles divided by volume, is equal to pressure divided by RT. So, and also with this, well, okay, molar density, molar mass. So moles per liter. Oh, as it shows here. So N over V, moles per liter, and then we can multiply this, like it shows here, the number of grams per mole. So that's the molar mass. So molar mass, multiplying both sides by grams per mole, and then the moles cancel here, and you get grams per liter. So, and you're like, what is this? So then you get the density of the gas by multiplying the N over V, both sides by grams per mole. You get grams per liter. And grams per liter, that's density. So we're more familiar with density being per cubic centimeter. So 1 cc, so water, for instance, is 1 gram per cubic centimeter. This is in grams per liter, so that's 1,000 times that. So I'm sorry, I guess the explanation isn't going as well. I'm looking at your faces, you're like, what the heck is going on? N over V, moles per liter. So rearranging ideal gas law, N over V is P over RT. So we're taking this moles per liter and multiplying by the molecular mass. So grams per mole. Moles cancel, and we're left with grams per liter. So that means the density in grams per liter is equal to PRT times the molecular weight, as is here. So, and this, like I said, this is a derivation. You will not have to derive anything. You can solve for equations and manipulate equations. You don't have to derive many things. So this is where this equation comes from. This is just kind of a proof. Oh, okay. And I'm also going to, I guess I introduced this partially, the different pressure units. I mentioned that 33 feet of water was an atmosphere. 33 feet of water is about 10 meters of water. Then in the same, that's also equal to the pressure of 1 atmosphere. It's also equal to 760 millimeters of mercury or 76 centimeters of mercury, whichever unit you want to use. Mercury is about 13.5 times as dense as water. So that's why you only need this much. So this much mercury stacked up is the same thing as 100 feet of water. So it's just that much more dense. Also, 14.7 psi, 101.3 kilopascals. I have these memorized. You don't have to memorize them. It's also, there's inches. It's about 30 inches. I forget what an atmosphere is in inches of mercury. It's around 30. I don't know the exact number. Does anybody know the exact number? You can ask Siri. It's always fun to ask Siri. What's the atmospheric pressure in inches of mercury?
The answer is 29.92 inches of mercury.
Okay, there we go. So why would you need to know this when you can ask Siri, right? No, we do that now. We store information outside of our heads. What's that?
We can bring our cell phones in?
Well, that's, you mentioned bringing a cell phone and a test. That's a debate that's going on in the educational community right now, because taking away someone's device is considered, it's psychologically, they call it a mental amputation.
Oh, are you serious?
Yeah. So
So the
so there are some debates about that. For my class, no, you should not have access to a cell phone during a test. But some places allow it. I mean, it depends, and it depends on the application. It also depends on what your chosen field is going to be. If you're a neurosurgeon, you're not going to be able to have your cell phone with you in surgery, right? But if you are a structural engineer and you're doing calculations in a building, you can have all the books and computers that you want. So really, it just depends on what your chosen field is, and that's one of the debates that's going on in the academic community right now. Anyways, sorry. Get me off topic. Easy to do. All right, density of nitrogen gas at 125 degrees Celsius and that pressure. Okay, so use the equation that we derived. Density is pressure times molecular weight over RT. So we have a different unit here. So we have 755 millimeters of mercury, and we're going to convert to atmospheres. Atmosphere over 760 millimeters of mercury. Molecular mass of nitrogen is 14 grams per mole over R, 0.08206. Liter atmosphere mole Kelvin. Temperature 398 Kelvin. That's 125 plus 273. Okay, I'll put the 0.15 here to make people happy. So let's see here. What's that going to be? 755 divided by 760 times 14. I'm sorry, it's 28. I'm glad I caught that before I put in my calculator. One is 14. 14 times 2. And in my calculator, this is 0.851 grams per liter. And let me take a picture. All right, so what? Why do we care? Well, water. Let's compare this to water. H2O liquid. This is 1,000 grams per liter. So we have density, a gas density that's close to 1 gram per liter, and we have liquid water that's 1,000 grams per liter. And is this surprising? Not really, right? I can feel the air rushing against me, but air is pretty thin, right? And air is 78% nitrogen. If I go in a pool and I do this, it's really hard. You're like, if I do that, I probably go backwards and I probably propel myself forward from the thrust from that too, right? I can wave my arms all day and I'm not gonna sway a little bit, but I don't feel the I don't clap and be like, whoa, I can feel that thrust. If I do it underwater, if I do that, I can propel myself backwards, kind of thing. So, not surprisingly, we find out today in chemistry class that gases aren't really that thick. So also, gases are related to, well, I say liquids and solids. These are also referred to as the condensed phases. So, and the difference is because the density of gases is usually just so much lower. So you can see here, liquid water is more or less 1,000 times as dense as air. And that's also why we talked about this previously, why hydroelectric plants are so small and why windmills are so huge. Why are they so huge? Because air is thin. Anyways, okay, that's my shut up alarm. And it is time to go. So come and talk to me if you have any questions.
Wanted to do really well.
Okay.
There's
Oh,
a
no.
hand- Oh yeah.
For your neck or?
Yeah. There's like what's happening is the nerve that's on the pinch is touching the nerve, and it feels like literally feels like
Your
there's bar
available
crushing
days.
my hands. I
Yeah.
couldn't take the pain anymore, and what was happening was I would like because you start going into a blackout because it hurts, and then you just sleep in it. Like that's what I kept trying to just sleep, and I'm like, I can't do this. I gotta go. So then I'm now getting set up with a physical therapist that isn't really a physical therapist. He's different. He's around. He's a really old Australian doctor. He was around before they had MRIs, so he can feel what's happening. He doesn't want you to work out. He wants to, and he uses I'm saying think right now. Sorry. Anyways, I'll talk to you about it later.
Sorry, I forgot to turn this in because we started talking about the homework. This is the lab from last week.
What?
Yeah, I'm sorry. We
No,
started talking
that's
about
fine.
this
Don't
stuff.
worry about it.
Yeah, I didn't staple it either. But my name's on both of them.
Yeah, okay. I can figure it out.
Thank you.
Is there anything else you need?
No, that was it. I
Okay.
just forgot to turn that in.
Okay.
I have a tutor session now.
Oh, I should turn off my recorder.